right, we're gonna get started a few minutes early. So I have been doing Advent of Code for a while, which is great. Finished problem 17, 18, something like that. 17, yeah, on Tuesday. And I will be continuing with it. But I also want to start doing, like, the problems take me longer than they used to. And so it's just, I don't know, it's, sometimes it's 2 or 3 videos for one problem. And it gets a little bit tedious somehow. So I will be finishing that out, but I'm going to kind of space those out. And instead, I want to start a series or continue a series. Like, my background is in math, and I've been a programmer, a coder for a long time. Worked at a tech company and so on, but really my background's in math, and I kind of often think of programming as a more of a tool than kind of something I'm interested in for its own sake. Whereas math to me is like at the core of everything, and that's sort of largely what I'm interested in. I teach a fair amount of coding, but I also teach math and physics and other things, and so basically wanted to continue the series that I'd done a little bit on before, where I went through the properties of complex numbers and how you can use complex numbers, basically give you a shortcut into all of the trig that you learn in high school, or at least all of the trig you learn in the U.S. in high school. I only went to high school in the U.S., so I can really only speak to that. And I really love complex numbers. I think they're really beautiful, and there's a lot of interesting stuff to be done there. And I came across something this morning, actually. I was digging around in some old math concepts that I remembered and realized I didn't know that much about. And I was reminded of the Eisenstein integers, which the Wikipedia for which is here. And the Eisenstein integers, or maybe first it's worth talking about the Gaussian integers. The Gaussian integers are just the integral complex numbers. So if you remember, complex numbers are on the real versus imaginary plane. So 3 plus 2i would be out here. But in general, you can have, any real values as the a and the b in a complex number. So you can have, 2 plus pi I if you want, right? Pi is not an integer. Well, the Gaussian integers are the complex numbers with integral coordinates. So they form a square lattice, right? So if you take all of them, they're all of the corners of the square lattice of the 1x1 grid centered on the origin in the complex plane. And they're super cool. You can factor them, and they have prime numbers, but the primes are not the same as the primes in the regular integers. They end up being, you can characterize them in terms of the primes in the regular integers, but things like the square root of 2 can be factored in the Gaussian integers, because you can have 1 plus I, for instance. Is that right? Yeah, 1 plus I times 1 minus I is going to be 2. So 2 can be factored. It's not prime, whereas it is prime in the integers. So there's some really cool stuff in here. Gaussian integers, already cool. But we're like pretty good at working with grids. It's very simple to use real numbers or a vector field to do that, x and y, Cartesian coordinates, all that. So it's like the Gaussian integers are cool, but they don't really give you I don't know, they don't kind of give you a new set of tools to do geometry in the way that, like, the complex numbers give you a new set of tools for circles and triangles. The Eisenstein integers, on the other hand, I think, do. So the Eisenstein integers are the same idea, but instead of using 1 and I as the two directions, you instead use 1 and plus or minus a third of the way around the circle. So geometrically is probably the easiest way to see this. We can look here. So obviously you can still go 1, but you can also go this omega, which is a third of the way around the circle. And then if you go another omega, you get another third of the way around the circle, and then back. And what you get from that are, 3 plus 2 omega is over here. But you get this triangular lattice, because you can get to, like, if you want to get to this, it's not that it's 1. Let's see here, what would this coordinate be? 1 plus omega, right, would be this coordinate here. So you get these equilateral triangles, so it's now a triangular lattice. But the thing I want to explore today is that inscribed in this triangular lattice are hexagons. And if you've ever tried to program something that involved a hex grid, like, say, if you know Settlers of Catan, the board game, if you try to program something where you're navigating around a hex grid, it's a pain. It's very doable, but it feels a little bit arbitrary. Like, there's a very cool, let me see if I can find it quickly. Yeah, so there's this guy put together this whole thing. It's basically a book with how to work with hex grids, and it's really cool. But like, there are 3 different coordinate systems, or 4 different coordinate systems. There's this really, really cool thing where you can use 3 dimensions. You can think of the hex coordinates as looking vertex on a cube. So here's your cube. You look vertex on. Each one of these is a hexagon, and so you can use this cube to define a bunch of hexes in this, like, 3-dimensional space with a redundancy. There's some really, really cool stuff in here, but it's like, you really have to tinker with it, and it's like kind of not worth remembering to me. Like, anytime that I ever had to do this, I would always just go find this guy's website and implement these things, which is all fine and well, but it's tedious. You end up programming the same thing over and over again, and it just doesn't feel like the simplest way. It feels like there's a simpler way, I guess. And so I have a hypothesis, and I've really not tested this. I looked at this morning. I was reading about Eisenstein integers because I could basically only remember the definition. I couldn't remember anything else about them. And I actually saw this picture, which are small Eisenstein primes. So these are the prime numbers in the Eisenstein integers. And I saw this hex, and I thought, man, I bet there's a really nice characterization and way to navigate hexes using Eisenstein primes. So that's what I want to look at today. I want to model the Eisenstein primes in Rust, and I want to see if we can use them to do these sorts of manipulations more easily in a hex grid. So let's jump to it. And I had already put together, for the previous video, I I'd implemented complex numbers, had I? Oh no, I just imported them. The thing about complex numbers this way is that they use floats internally. I don't think I want to use floats internally. So I think what I'm going to do, I fired up a new repo. And I think we're going to start over. Or we're going to start by implementing the Eisenstein integers directly. We're not going to implement them in terms of complex numbers. We'll see. We'll see if it's easier or harder. I also brought Bevy and into this because, I think the best way to make sure that something like this works, like we'll write some unit tests, but I think the best way to make sure something like this works is to actually, code up a little thing. So, let's just get started and see how we do. So jumping in, definition, the Eisenstein integers, do they have a symbol? Is there a name for the set? No. Doesn't seem like it. Okay, well, we'll call them E. Are the set A plus I. I don't really want to use omega, so I'm gonna say W. Okay, that's wrong. A plus BW, where W is the first third root of unity. E to the what would it be? Tau I over 3. By the way, if I wrap these, I can't remember. Can I do text in here? Markdown, open preview. Hey, I can. Very cool. Should probably be capital T, huh? Nope. It's lowercase t. Okay, looks small, but that's fine. Okay, and just recall that when you raise I to an imaginary number, which tau I over 3 is, then the coefficient in front of the I, and sorry, yeah, you raise e to an imaginary number, the coefficient in front of the I, which is tau over 3, so 2 pi over 3, tells you how far around this unit circle you go. So this is 1/3 of the way around the unit circle, going counterclockwise. So they form a triangular lattice on the complex plane. Get rid of the colon here. And let's say goal, use Eisenstein integers to model a hexgrid navigation around a hexgrid. Okay. So it's probably worth types, or let's just say API. So we would expect to have Eisenstein, which would be a struct How do I do code snippets? Is it this? Let's forget my markdown. Or maybe I do like code rust and then markdown code block, extended syntax, code block. Code block. Oh, interesting. So if I just do this, oh, huh, I didn't know that. Okay. A, and this will be, let's just say U32. B is U32. And then we'll make Eisenstein's should be addable, multipliable, and so on. And then we'll, in fact, we can just say they should be add and mul. And then we also want hex. And the hex should be represented by the point in its center internally, but externally Eisenstein. And we'll say hex is represented internally by the point at its center, but exposes a series of operations to navigate in terms of hexes. That's the basic idea. The goal will be to hide the fact that under the hood there are Eisenstein integers, but make it really easy to implement this, and make it easy to implement in a way where we don't have to memorize anything, because it just makes sense, right? We want hexes. We construct hexes out of triangles because triangles are, well, because hexes can be constructed out of triangles. And so how are we going to do that? Well, we'll use a hexagonal lattice. How do we model a hexagonal lattice? Well, we'll use Eisenstein integers. Maybe I just call this Eisenstein integer. Okay. I think this is a cool start. Allergic term, please don't advertise on my channel. Okay. Okay, let's get to implementing this. So, let's say new folder Eisenstein, or hex, let's say hex. And within this we'll need mod.rs, and we will need and we'll want Eisenstein.rs, and we'll want hex.rs. Okay. And in here we'll have So, pubstruct Eisenstein integer A U32 B U32 impl Eisenstein integer, and okay. Do you want this? And I want to be able to add things. We should do tests though. Test mod. Test Eisenstein. It takes every bit of willpower I had not to write Einstein every time I write Eisenstein. Features add. And so we'll say let x be sure, assert equal, x plus y is Eisenstein 4 and 6. Just thinking if there's ambiguity in Eisenstein integers. So if we try to add, let's see here. Let's look. Unity, triangular lattice. I'm just trying to think if you can ever have some point that can be expressed in multiple ways. No, the answer is just no, right? Because I could have a map that turned Eisenstein integers into Gaussian integers by, you know, shifting, like skewing all of these lines. Like there's some matrix that probably does it. Okay, so there shouldn't be any ambiguity there. So this should be fine. Maybe let's also do an example that's negative -1, -2, and sure. -6. All right. Let's do something similar for multiplication. There's multiply. And here, again, I wonder, is the multiplication the roll the same? No, it's not. What's the multiplication roll? Let expected be. How does multiplication work here? coordinate wise. Multiplication satisfies what? What does it satisfy? So if we want a plus b omega times c plus d omega, then we're going to have AC plus AD plus BC omega plus BD omega squared. And omega squared is equal to something. Note that omega squared is, so omega squared is two-thirds of the way around the circle. Right, so omega squared is this, which is equal to -1 minus omega, right? -1, negative omega. So -1 minus omega. And we can say, therefore, multiplication satisfies this same thing, except that this becomes -1 minus omega, which means we get AC minus BD plus AD plus BC minus BD. Omega. Which is kind of interesting in its own right. BD shows up twice and so on. Okay. So what do we expect to be the case here? In our expression, we expect it to be expected A to be, I think that's right. Expected B, that's wrong. It should be, so AC, yep, minus BD is correct. But then AD, plus 2 times 3 minus 2 times 4. That's what we expect. So let's let expected be Eisenstein integer new expected B. And we make them okay. What else? just check that x times Eisenstein integer 0 should be 0. Good. And 1 should be x. Also good. It's interesting that GitHub Copilot sees the pattern, but thinks that these are just complex numbers. They're like close enough that GitHub Copilot just thinks I'm implementing complex numbers. Okay. What else? I mean, these are probably the big things. We'll want to render them eventually, but I think this is a good starting point. So let's add for Eisenstein integer. That looks good. Let's impl add U32. And let's impl add Eisenstein integer for U32. I don't think I'm allowed to do this. Unless I am. But I don't think I am. But we'll find out. And then impl mul for Eisenstein integer. And I assume it's going to get this wrong. Ooh, it got it right. Wow. A times C minus B times D. A times D plus B times C minus B times minus B times D. Yeah, that looks good. Mul for mul U32. Oh, why are these U32s? They should be I32s. Whoops. Let's fix that. U32 needs to be I32 everywhere. Okay. And then impl mul this. I like it. Okay. Cool. And then what else? We need 0 and pub function 0. Whoops. And pub function 1. Good stuff. I guess we can do pub function omega also. And let's go ahead and assert in here, let's say assert equals Eisenstein integer omega times Eisenstein omega should be minus 1 minus should be Eisenstein minus 1 minus 1. Okay, let's get this out of my way. And drive some stuff. Yeah, I guess we want default also. Default seems fine. It's also hashable and all that stuff, but we can add those if we need them. And yeah, here we need parens. And here we need parens. Okay, let's try to test this. And they pass. Very cool. Okay, so we have basic Eisenstein integers. So we try rendering these immediately. But let's do the hex stuff first. So here we're going to use create hex Eisenstein pubstruct hex and Eisenstein integer. Let's go ahead and drive some stuff here too, and then impl hex. I don't really want to expose these. Can we derive add? No, right? Okay, I think so. Okay, let's just impl add for hex, because that's totally reasonable. That has the right interpretation. And test hex, hexes add, just thinking about what else we want in this API, but I think sure. It's a fine test to have. Let's say hex gets neighbors. So let's let origin or center hex origin. Oh, by the way, did I do something really bad with my? Yeah, we don't. This is wrong. Hex origin, assert equal center, get neighbor, hex direction above. And it's not gonna be 0, 1. Which, by the way, I don't want don't want a new function here. Let's call this from Eisenstein. And Eisenstein, and it's not going to be 0, 1. It's going to be what? So here's the hex. So the center of the next hex is +2. It's at 0, 2. The hex to the left is going to be at -2 omega. The hex to the right is going to... Oh, there is no hex to the left. I mean, there is, but the hex to the left... So imagine this is the center hex. So +2. And then to go above and to the left, you go -w minus... Or +1 minus w. No, +1 plus w. And so on. Okay. So 0, 2. Let's do 6 of these. And where does this say center? These need to be dots. And then we'll say below. We'll say left above. This is going to be 1, 1. Left below is going to be -2. Let's get here. Wait, this is wrong. This is wrong. Hang on. Above is 1 plus 2w. One plus 2w. Below is -1 times 1 plus 2w. And then -1 plus w is left above, so -1 plus w. And left below is the same thing. No, that's not right. This isn't right either. Okay. 1 plus 2w. 1, 2w. Good. Below is going to be here, which is 1, which is -1 minus 2w. minus 1 minus 2w. Yeah? Yeah. And then here is minus 1 plus w. Good. Here is minus 2 minus w. And then right above and right below is going to be this one, which is plus 2 plus w. And right below is going to be this one, which is plus 1 minus w. And this, is this right? I think this is right. Okay. So let's take this and use it to create hex direction. Pub enon hex direction. And it's going to be all of this. And we want to just say, how do I do regex? There, regex, find, replace. Just a normal substitution command. Looks like it's normal regex. So this becomes what, dot star lazy get neighbor this, and then you know what, let's actually not do this with a search. We can do it easier than that, because we can do it with this. Almost. Oops. And then these just go away. Right, and we don't need these either. Oops. Okay. And let's derive all the things. Default does not need to be here. Okay. So that gets us hex direction. We need origin, and we need from Eisenstein. Okay, so from Eisenstein it's easy. Function origin. Oops. Origin. Good. And get neighbor. Function get neighbor. Self. Direction. Hex direction. Returns a new hex, and it should be this. Yes. And why don't we like adding these? Can't add If I just put this in here, does it? No, it doesn't. Okay. Add hex for hex. And same thing, add hex for hex. There's maybe a better way to do this using from, but should be all right. What's the issue here? Eisenstein integer AB. It's private new. Okay, cargo test. Have a failure. Right below, we're saying is 1, 1. So right below should be 1, negative 1. All right. Let's go ahead and commit this. Basic Eisenstein and hexes. Okay. And let's go ahead and rename this the whole thing. Okay. So, what to do now? Maybe we just start rendering these things. I just realized one tricky thing. My thought was to do the rendering in Bevy, but I don't know that Bevy has native hex shapes, and I'm not sure I really feel like fiddling with the, let's see here, Bevy hex. Just looking to see if geometry. looking for where this is rendered because I'm quad indices. Does Bevy have a line? Drawing basic shapes. Arbitrary rectangles. I wonder if I actually want to use Nanu for this. A little bit nicer. It's just easier to draw stuff. Yeah, I think maybe I do. Okay, in that case, Rust Nanu. So let's get rid of the stuff we don't need, which is, hey, all of that. Oh, except Rand. Rand might be useful. Make sure this still builds. And while that's building, let's figure out the docs. Draw, what happens if I say hex? Cube. I mean, I know it at least has lines, so hexagon. Okay, line. Primitive, draw a line, sure. Polygon. Polygon should be good. Begin drawing a polygon. Okay, so it's still building. Polyline. No, polygon is fine. It'll enforce that it's closed. Let's add a function to Eisenstein that says test Eisenstein integers get complex plane get coordinates. And let's say assert equals Eisenstein integer new. Let's just say 0. Should be 0, 0. This is what's going to allow us to draw it on the screen. spot, like new 1734. And then here we'll have pub function get coordinates, and yep. Sweet. Okay, and then we can do the same thing for hex. Get neighbor, pub function, get coordinates, self, F32, and it's just self dot 0 dot get coordinates. Okay. Test. Good stuff. Module, pubmod render, and we will have render.rs, and in main we will have mod render. Okay. And in render we will steal something from some example. Whoa, these are really cool. Very, very cool. Welcome, blah, blah, blah. I'm pretty sure I remember an example with a hexagon. So I'd like to just steal that. Here's an ellipse. Whatever, let's just fire this up. And then we don't want main here. So let's get rid of this. And in main, we will have this. We'll say use standard prelude. And then in render, we need to expose a few of these things. So let's make this a public function. Public function probably also needs to be a public function. And in main, we say use create render those. No model in render. Render. Could not find render in render. Private type model. Yeah, we want this to be public. Okay. So this is just as a smoke test for Nano. Nano, if you haven't seen it before, I've used this in other streams, other videos, but Nano is a really fancy low. It's a really nice way to do like simple visualizations quickly in Rust. It's meant for kind of procedural art, which is cool. Does a bunch of cool stuff. But I like it because, like, as opposed to Bevy or something, you can just get a visualization up and running really quickly. Okay. So we have our smoke test, but now we want our hexagon instead. So let's say hexes, vec hex. Seems important that we create hex, hex, hex. So we'll get an app window, and we'll say for now, let's just say hexes equals a vec with hex origin in it. I don't know what this is, but whatever. And then for now, let's just say hexes. This is fine. And in view, instead of drawing hexes, we will draw a polygon. So hex should know how to give its coordinates. So let's call this get center coordinate. And then we're also going to need each of the edges. Which I just had an interesting thought, which is that the centers, is this true? So the centers of the, no, it's not true. It's just each thing that's one unit away. So maybe what we'll do is say test Eisenstein integers get neighbors, and here we'll just say assert equal one zero zero one negative one negative 1 1 is not, so it should be certainly 1 0 negative 1 0 are up and down. Or, no, sorry, are left and right. And then let's just say this and this, and then 1, 1 is right, and -1, -1 seems right. -1, -1, yeah. Okay, it's those. And it should be not a vec into iter collect. Which reminds me that hex, I didn't do it that way. Right. Okay. Cool, so let's import hash set, and let's implement get neighbors. Self, hash sets, self. Nope. I mean, I think we basically just return the test, which makes this not a very valid test, or not a very useful test, but whatever. Hash set self, get rid of this, get rid of this, collect is fine, and then this goes. And why don't we like hash set? Oh, because it got imported to the test. And why don't we like collect? No, into iter, that should be fine. Why don't we like collect? Derive. Oh, hash isn't satisfied. All right. And now test. Okay. And now Eisenstein should also be able to get all of its, I guess Hex should be able to get its coordinates now. So let's say test Hex gets vertex coordinates, and let's say let Hex sure assert equals center dot get edges dot get vertex coordinates, and this should be, let's do it multiple lines. Let's this should be some vector do iter collect, and what's it gonna be? It's gonna be not those things. It's gonna be 1 0 -1 0 0 1 -1 0 or 0 -1, and then 1 1 and -1 -1. And then let's say let above left, or left above, and here we can assert equals center dot get coordinate center coordinates. So left above will be at -1, 1. And vertex coordinates, and I'm going to trust that it did the math right. Looks like it. Whoops, I think I'm missing some semicolons. And get vertex coordinates. A function get vertex coordinates. Self should return a hash set of F32 F32s. And this is going to be what? It's going to be definitely not doing whatever this is. It's going to be it's going to be the Eisenstein center. So it's going to be self.0 dot get neighbors dot into iter dot map get coordinates collect. And what's the problem? And do we really not, we can't infer this? Oh. Sure. And if we want to put this in a hash set, it has to be hash. Which is fine. And what's going on? F32 doesn't satisfy hash. That's fair. Maybe I kind of want these in order also. I think I do, now that I'm thinking about it. So let's actually call this a vector. Let's, collecting here is fine. This is not fine though. And we want these in somewhat different order. So starting to the right is okay. Then we want to go to 1, 1. So we want this. Then we want to go to 0, 1. Then -1, 0. Then -1, -1. We want this. And same thing here. If I X all this out, will GitHub be nice to me? 0, 1, 0, 2. Yes, GitHub was nice to me. Okay. This is wrong. This needs to be left above. And this needs to be left above. Okay. And then Eisenstein. Probably just gonna do a get ordered neighbors kind of thing. So let's say it's this. -1. the order here? 1 0. Then it should be 1 1. So -1, then -1, -1. Yeah, this is right. Let's get rid of this, and let's rename this get ordered neighbors, and it'll just return a back. Get rid of this. 1 0 1 1. -1 -1 0 -1 -1. Okay, guaranteed I messed that up somewhere. Okay, we're fine until we're not. Self.0 get ordered neighbors. Well, this is definitely wrong. To iter map. There we go. That's why we have tests. Okay. So now in render, we should be able to say draw polygon points and it's not going to be this, it's going to be an example of using polygon. Do we have one of those? Begin drawing a polygon. Polygon init. Polygon init. Polygon. Can I see an example? New. Polygon. A new polygon. Drawing 2D shapes. Polygon. There we go. Points. Okay, so points seems like it's just a vector of something. So let's say vertices. And we'll say for hex in model hexes. Oops. Yeah, I don't really care. Let's just move this up here. Let vertices be hex.get vertex coordinates. Is this sufficient? Oh, it is. Nice. It knows how to convert. Okay, cargo run. See what happens. Okay, there's a little tiny something in there. But it's because this is probably in terms of pixels. So let's just add a scalar for now. Const. Let's call it coordinates 2 pixels. 50 seems sane. And we'll say dot into iter dot map p times coordinates 2 pixels dot collect. Can't multiply. Sure. And it's going to be p dot 0 and p dot 1. Vertices doesn't know what it is. Vertices still doesn't know what it is. Because syntax. Okay. Test. Cargo run. Okay. That's a start. That isn't what a hexagon looks like. A regular hexagon, anyway. So, what happened? So there should be a symmetry, so it shouldn't matter how the. I do think I think Nanu might go from the top left down. Window coordinates 100, 100. Oh no, it goes from the bottom left. X and Y are at the center, increases towards the right, decreases towards the left, increases upward. Okay, cool. So those are right. Let's look at hex. Vertex coordinates. So 1, 0 is that way. Hang on. 1, 1. Wait, this is wrong. Okay, I see what the problem is. These are meant to be actual coordinates. Which they're not. So, neighbors, okay. So, get coordinates. This is not how these are meant to work. 0, that's correct. That's correct. This is wrong. So, this should be... let's pull in complex numbers, I guess, to do this easiest. Complex new maybe polar or something. Complex exponent complex tau, something like this. Num tau, let's just do tau over 3 times complex I. Something like this. Okay, and then it says what the hell are you talking about? And we look and find out how we do complex numbers in the past. What did we use? This is not the right repo. This is the right repo. Okay, so thing number 1 is, let's pull in F32. Thing number 2 is, let's pull in complex. Non-complex, and okay, and this should now be correct. So it's, let's see here, let's call this, let omega complex be this, and then omega complex dot a dot real, omega complex dot imaginary is what we want. And here, complex. How do we take things to a power? Complex new dot exponent. So we need to do this, which that I believe should be a complex number, and then we exponentiate it. Complex I. Okay. And this won't be right either. This should be 17 plus 34 times complex I. Let 2 as complex be this, and then it's as complex dot real and as complex dot imaginary. Okay. Complex F64 seems very reasonable. Or, yeah, whichever. Doesn't really matter. Okay. So, obviously, that means that this needs to change. So this is going to change to this plus this times complex I, but as complex complex be this. And then we return as complex dot real as complex dot imaginary. Okay, so the point is to render it into a no, this is still not right. It's gonna be times self dot complex as omega. Omega is complex. Omega as complex. Alright. And so this is wrong. This should be omega complex. And this is what we will do. A function omega as complex, complex F32, and it will be this. Okay, cargo text. Expecting some failures here, I think, because of the way I did the hexes. Yeah, like this is going to be wrong. What it should be, though, is Eisenstein integer new of these things into iter map. Sure. And likewise here. New and okay. Left above get vertex coordinates and again into iter map. And what's going on here? Okay. Still one failure. Get center coordinates. Yeah, I mean, this should be Eisenstein integer new. Get coordinates. Okay. Cargo run. There we go. We have a hexagon. Let's add add some other hexagons. Let's see here. Let's say origin hex be this, and then we'll do origin hex dot get neighbor above, and origin hex dot get neighbor right below. Now we expect 3 hexes. Look at that. Above, center, and right below. So there we go. I mean, in 2 hours and like an hour and a half, we were able to, without really looking anything up. I mean, I had to look up some APIs, but I didn't need to look up the algorithm for locating hexes. I didn't have to look up all the different weirdo coordinate systems. There's just this very sensible coordinate system where we use the fact that the Eisenstein integers are a triangular grid, and we turn them into and we use the fact that within a triangular lattice is a hex grid, and then we can just implement the hex grid very easily on top of the Eisenstein integers, which I think is pretty cool. Now there are various things you end up wanting to do. Like get shortest path distances. And I'm thinking, so one thing is that you can compute the distance between 2 hexes now by just taking the norm of their underlying Eisenstein, like the difference between their Eisenstein distances. Because there's a well-defined distance on Eisenstein integers. So that you get for free. Finding the shortest path through some hexes is an interesting puzzle. I'm just trying to think whether there's something slick we can do. I mean, certainly we can do normal pathfinding algorithms. So, like, if we had a set of polygons, a set of hexes, and we wanted to find the distance between 2 points, we have some complicated thing. Since we know our neighbors, we can use, like, Dijkstra's algorithm, for instance. Because in general, you can have some crazy, you could have some setup where the hexes really don't, they're really not convex, so you have to go way out of your way in order to get to your destination, so you still have to do Dijkstra's algorithm, but you don't have to run it on these wonky coordinates because you've got nice coordinates available to you. I also imagine that if you wanted to, it'd be easy to convert these coordinates into the ones that are used, say, in that book that I opened up at the beginning. Excuse me. I'm just thinking if there's anything else super interesting to do here to demonstrate the power of this. Yeah, I mean, I think this is a pretty good place to stop for the time being. This pretty clearly works well. Is easier to remember, at least for me, makes a lot more sense than all of the other ways to give coordinates to hex grids. And I hope this has been interesting to folks. I think I'm going to be continuing with this, or continuing with some related stuff in the next few videos. So yeah, let me know what you think. Let me know if this has been interesting or useful to you. Subscribe or follow if you haven't already, please. It helps me out. And I will catch y'all next time. Have a good one.